What if I told you that a tiny space rock floating between Mars and Jupiter could be the key to understanding how planets form? Not just that, but this same rock once tried to become a planet itself, only to be stopped by something as massive as Jupiter. Sounds like a sci-fi story, right? But it's real. And it all began with a mission called Dawn. In this video we're diving deep into NASA's incredible journey to visit two mysterious asteroids, Vesta and Ceres. You'll see what was discovered, what shocked scientists, and how a revolutionary spacecraft made history with its high-tech ion engine. Back in 2011, excitement filled the astronomy world. For over 2 centuries, humans had known about large asteroids in the asteroid belt, but they had never been more than distant points of light through a telescope. The first asteroid ever discovered was Ceres in 1801. Not long after, Pallas, Juno, and Vesta followed. Believe it or not, by 1845, people actually believed our solar system had 11 planets. That included Mercury through Uranus, since Neptune hadn't been found yet, and those 4 newly discovered asteroids. But as more asteroids were identified, scientists realized they couldn't all be classified as planets. That was lucky because today we've cataloged millions of asteroids, ranging in all shapes and sizes. Before 2011, not a single one of those original 4 asteroids had ever been visited up close. That changed with the Dawn spacecraft. Launched in 2007, Dawn had a groundbreaking mission. It would explore not just one but 2 of the biggest asteroids, Vesta first and then Ceres. What made this mission so revolutionary wasn't just where it was going, but how it would get there. Its trip to Vesta took 4 years, and along the way it used a gravitational slingshot around Mars to pick up speed. On the surface that sounds routine, but what made Dawn special was the technology packed inside its sleek body. Dawn wasn't powered by a typical rocket engine. It ran on an ion engine, a cutting-edge propulsion system that changed the game. NASA had already tested this tech on a previous spacecraft called Deep Space One. But Dawn pushed the boundaries even further. It became the first spacecraft ever to go into orbit around 2 separate celestial bodies. Unlike regular chemical rockets that burn fuel fast and create powerful bursts of speed, Dawn's ion engine was all about endurance. It used electricity to ionize xenon gas, turning it into high-speed particles that exited the engine at 150,000 kilometers per hour, giving Dawn a gentle but continuous push forward. This constant, efficient thrust allowed Dawn to slowly but surely build up speed over time. It wasn't quick. Dawn needed 4 whole days just to accelerate from 0 to 100 kilometers per hour. But the key was in the long haul. Over time that gentle push added up. During its journey to Mars, Dawn kept its engine running 85% of the time. In that span, it used only 72 kilograms of xenon fuel and gained over 1.8 kilometers per second in velocity. When it finally arrived at Vesta in July 2011, the spacecraft began sending back images that stunned scientists across the globe. Vesta looked nothing like they expected. After entering Vesta's gravity, Dawn lowered itself into a closer orbit to get a detailed view of this asteroid. Right away Vesta's shape stood out. It didn't look like a smooth sphere, it looked squashed and deformed. That's partly because it isn't very large. In astronomical terms, even these giant asteroids are still tiny. Vesta is only about 500 kilometers across, which gives it a surface area similar to the size of Pakistan. That's small compared to our moon, yet it still accounts for about 9% of the entire mass of the asteroid belt, showing how spread out these space rocks truly are. Another reason for Vesta's odd shape is its violent history. Over 1 billion years ago, it suffered 2 massive collisions near its south pole. These impacts weren't small, they were planetary in scale. They left behind enormous craters, cutting so deep they reached the asteroid's mantle. The outer layers cooled and hardened over time, leaving behind a giant crater now known as Rhea Silvia. Because the impacts overlapped, Rhea Silvia is the newer and more visible one. Like other complex craters, Rhea Silvia features towering terraced walls and deep trenches, some of which are bigger than the Grand Canyon. At its center lies a massive peak, once believed to be the tallest mountain in the solar system. That title later returned to Olympus Mons on Mars, but Rhea Silvia's central peak still rises an impressive 20 to 25 kilometers and stretches over 100 kilometers across. Considering Vesta's small size, this mountain appears like a giant pimple at its south pole and is easily visible from orbit. The 2 colossal impacts that shaped this region also blasted an enormous amount of rock into space. So much, in fact, that debris from Vesta was scattered throughout the asteroid belt. These fragments are now recognized as their own group, called V-type asteroids, and they all trace back to those ancient collisions. But the debris didn't just stay in the belt. It spread across the entire solar system. Incredibly, about 5% of all meteorites that land on Earth are believed to have come from Vesta. These are known as Howardite, Eucrite, and Diogenite meteorites, or HEDs for short. That's right, we've been studying bits of Vesta without even needing to bring samples back from space. By examining their structure and chemical composition, scientists have learned a lot about Vesta's formation. Dawn's data confirmed that Vesta is unlike any other asteroid. It's the only known rocky protoplanet still in existence today. What's a protoplanet? It's a baby planet that started to form in the early solar system but never made it all the way. Billions of years ago, dust from the early solar nebula began clumping together into thousands of these planetesimals. Over time they crashed into each other, growing larger and forming planets. Our moon, for example, is thought to have been created when a Mars-sized object named Theia collided with Earth. The resulting debris eventually formed into the moon. Vesta had a similar beginning. It underwent heavy impacts, built up heat inside, and for a while even had a molten mantle and a dense core of iron. Today that iron core is believed to still exist, about 220 kilometers in diameter, similar to the cores of terrestrial planets like Mercury, Venus, Earth, and Mars. But over billions of years, Vesta's interior cooled and hardened. That's why it never finished becoming a planet. By modern standards, it might qualify as a dwarf planet, except for one thing. It's not round. One of the criteria for dwarf planets is that they must be shaped by their own gravity. But Vesta's violent past changed that. Those massive collisions happened long after it had cooled, leaving it too stiff and rigid to smooth itself out into a sphere again. So, what stopped Vesta from becoming a full-fledged planet? Scientists believe Jupiter played a major role. Its immense gravity may have pulled material away from Vesta during the early stages of planetary formation. Or it may have disturbed the area enough to keep Vesta from collecting more mass. Either way, Vesta never had the chance to grow. If you look at Vesta with the naked eye, it seems pretty bland. But that's deceiving. Using specialized cameras that detect a wide range of wavelengths, Dawn revealed a complex and colorful world. Different colors highlight different types of materials, many of which were created by ancient impacts. For example, dark patches might be debris from past collisions. Reddish areas could be molten rock that cooled into new surfaces. Dawn even spotted unexpected signs of past flowing material on Vesta's surface. In one image, a small crater has what looks like a flow channel spilling from it. The colors indicate the material is different from its surroundings, suggesting something melted during the impact. We're not entirely sure where this material came from. It might have been part of the impactor or melted rock from Vesta itself. These surprising details made Vesta much more dynamic than scientists had imagined. One of the most puzzling finds came from a young crater named Marcia. Near the bottom, Dawn discovered something called pitted terrain, areas where the ground is covered in small pits and holes. The only other place we've seen this kind of terrain before was Mars. Scientists think these pits may form when rocks containing water are suddenly heated by an impact. The water inside vaporizes and bursts out, leaving behind tiny craters. That kind of terrain shouldn't exist on Vesta, a world thought to be bone dry. Yet there was another mystery that Dawn brought to light. Marcia crater, by the way, is part of a larger feature that looks like a snowman on Vesta's surface. What's particularly interesting about the terrain around these craters is its unusual smoothness. This phenomenon is thought to be caused by a blanket of ejecta that covered the area after the impacts. When an asteroid strikes a surface, it often sends debris flying in all directions, and this debris can settle in surrounding areas, smoothing out the landscape. The smoothness of the craters on Ceres, coupled with their relatively shallow appearance, suggested that the dwarf planet's surface had undergone some form of resurfacing. This resurfacing could have been driven by internal geological activity, suggesting that Ceres was not merely an ancient, inactive body, but one with a complex and dynamic past. This discovery raised questions about how long Ceres had been geologically active and whether it still is today. The Dawn spacecraft, which made this discovery, spent only about a year in orbit around Vesta before it left the asteroid's gravitational pull and began the second leg of its journey toward the dwarf planet Ceres. Using its ion engine, Dawn built up enough speed to eventually escape Vesta's gravity and set course for Ceres. The spacecraft's journey was long and arduous, but the excitement in the scientific community was palpable as it neared its next destination. Dawn's arrival at Ceres was eagerly anticipated, as the dwarf planet had remained an enigma for decades, even though it had been studied from afar using telescopes, including the powerful Hubble Space Telescope. The best images we had of Ceres prior to the arrival of dawn were blurry and left much to be desired. Ceres appeared as a vague, featureless blob, and scientists were eager to see whether the spacecraft could provide the detailed data necessary to unlock the secrets of this intriguing world. NASA's Dawn mission began in 2007, and after 2 years of travel, the spacecraft reached its destination. The closer Dawn got to Ceres, the more detailed the images became. As the spacecraft passed through different orbits around Ceres, it sent back images that gradually revealed more and more of the surface. The most striking feature that emerged was the appearance of bright white spots scattered across the surface. These spots sparked widespread intrigue. No one knew what they were or what caused them, and many scientists speculated on various explanations, ranging from salt deposits to water ice. These spots were unlike anything observed on other bodies in our solar system, making Ceres a particularly interesting subject of study. Over time, Dawn's camera captured higher-resolution images, and the presence of multiple bright spots was confirmed. This discovery was significant because it suggested that Ceres was more geologically active than scientists had initially assumed. As Dawn's investigation continued, the spacecraft revealed a surface marked by scars from impacts, with craters scattered across its face. However, there were not as many craters as scientists had expected, especially considering the size and age of Ceres. This anomaly, combined with the bright spots, led researchers to conclude that Ceres might still be undergoing some form of geological resurfacing, potentially from subsurface processes. The discovery of these bright spots hinted at a far more dynamic and complex world than scientists had initially predicted. The bright spots on Ceres, which were first observed in 2015, were initially thought to be simple reflections of sunlight off ice. However, further observations made it clear that these spots were not simple reflections but instead were complex surface features with much more to reveal. The spots were most prominently located in the middle of craters, indicating that they were likely related to some kind of ongoing activity beneath the surface. One of the most significant spots, known as Spot 5, was observed in 3D using Dawn's data, revealing that it was associated with a peculiar haze. This haze was thought to be a sign of cryovolcanism, volcanic activity involving the eruption of water, rather than molten rock. Unlike regular volcanoes on Earth, cryovolcanoes erupt frozen materials, such as water ice, ammonia or methane. On Ceres, it was believed that the eruptions of ice and salts had formed these bright spots. Another intriguing feature observed by Dawn was Ceres' smooth surface in the vicinity of these bright spots. This smoothness suggested that a process was actively reshaping the surface, as previously mentioned. The most likely cause of this resurfacing was cryovolcanism. When a cryovolcano erupts on Ceres, water, mixed with salts and other chemicals, is expelled from beneath the surface. Upon reaching the surface, the water quickly sublimates into vapor, leaving behind a deposit of salts, which is why the spots appear so bright. The presence of salts on the surface also provided an important clue about Ceres' subsurface composition. As we delve into the composition of Ceres, it becomes apparent that the dwarf planet is not entirely like other asteroids in our solar system. While most asteroids are composed primarily of rock and metal, Ceres is much more similar to a comet, consisting largely of water ice. This makes sense considering its location in the outer regions of the solar system, where temperatures are low enough for ice to exist in solid form. While the surface of Ceres is rocky, it also has a considerable amount of ice beneath its surface, which could play a role in its geological activity. In fact, scientists believe that the interior of Ceres contains a large amount of water, possibly in the form of a subsurface ocean or large pockets of slushy, icy material. The presence of water ice on Ceres is significant because it suggests that Ceres might have the necessary ingredients for life, at least in a microbial form. Water is essential for life as we know it, and its presence on Ceres has led scientists to speculate that the dwarf planet could harbor some form of simple life beneath its icy crust. This idea has been further bolstered by the discovery of organic compounds on Ceres, which could potentially serve as a building block for life. However, the search for life on Ceres remains speculative, and much more research is needed to determine whether life could ever have existed on this distant world. The bright spots on Ceres also played a key role in revealing the planet's unique surface features. Many of the craters on Ceres were not as well defined as scientists had anticipated. Some craters showed significant signs of erosion, with softened edges and collapsed rims. This erosion suggested that, over time, the surface of Ceres had been altered by internal forces. A striking example of this is the large, relatively young crater called a crater. A crater is home to one of Ceres' brightest spots, and scientists believe that its central peak may have formed as a result of an internal upheaval, possibly tied to the cryovolcanic activity occurring below the surface. The occurrence of such features points to Ceres being a more geologically active world than scientists had initially expected. The fractures observed on Ceres further suggest that the planet is not a static, unchanging body. Instead, Ceres appears to have experienced significant stress within its crust. Some of these fractures were relatively young, while others were older. These fractures ranged from wide, deep fissures to small, narrow grooves. Some were thought to be the result of stretching within the planet's crust, while others appeared to be caused by compression. The presence of these fractures provided further evidence that Ceres had experienced geological activity over a long period of time, and possibly continues to do so today. One of the most fascinating discoveries made by the Dawn spacecraft was the observation of a large mountain known as Ana Mons. This mountain is approximately 20 kilometers wide and stands about 5 kilometers tall. What makes Ana Mons so intriguing is that it is located in a relatively flat area of Ceres and does not appear to be associated with any impact or other surface features. This has led scientists to speculate that Ana Mons may have been formed by a process called cryovolcanism. It is possible that water and other materials were expelled from the interior of Ceres in a massive cryovolcanic eruption, forming the dome-shaped mountain. If this hypothesis is correct, Ana Mons would be one of the largest cryovolcanoes ever discovered, making it an important feature for scientists to study further. In addition to the discovery of cryovolcanism, the Dawn mission also provided valuable insights into Ceres' internal composition. Based on the spacecraft's observations, scientists have developed models of Ceres' internal structure, which suggest that the dwarf planet may have a rocky core surrounded by a thick layer of water ice and organic materials. This composition is quite different from that of many other bodies in the solar system, and it raises important questions about the formation of Ceres and its potential for hosting life. The Dawn spacecraft's mission came to an end in 2018, when it ran out of fuel. By this point, the spacecraft had provided scientists with an unprecedented amount of data about Ceres, including detailed images, spectroscopic measurements, and other crucial data that will continue to shape our understanding of the dwarf planet for years to come. Although the spacecraft is no longer operational, its legacy lives on, and scientists are continuing to analyze the data it collected, looking for new insights into Ceres' history and its potential to harbor life. As of now, Ceres remains one of the most intriguing and mysterious bodies in our solar system. With its combination of geological activity, water ice, and organic compounds, it is a prime candidate for future exploration. Ceres may not only provide important clues about the early days of our solar system but could also offer insights into the potential for life beyond Earth. The Dawn mission has laid the groundwork for future missions, and our understanding of Ceres is only just beginning to take shape. The discovery of Pluto and its moon Charon before 1992 marked a pivotal moment in our understanding of the solar system's outer reaches. Pluto, discovered in 1930, and Charon in 1978, were only later confirmed as objects in the Kuiper Belt after 1992. Since then, thousands of Kuiper Belt objects, KBOs, have been identified, populating the vast region beyond Neptune. To truly grasp the scale and position of the Kuiper Belt, we can take a hypothetical journey in a spaceship from the Sun and travel outward toward the farthest reaches of the solar system. Along the way, we will compare the Kuiper Belt with the better-known asteroid belt and the more elusive Oort cloud. Our journey begins near the Sun, where we quickly zip past the rocky planets: Mercury, Venus, Earth, and Mars. Between Mars and Jupiter lies the asteroid belt, a collection of leftover materials from the formation of our solar system, a relatively thin and spread-out ring of rocky debris. The asteroid belt lies about 2.2 to 3.2 astronomical units, AU, away from the Sun and spans roughly 1 astronomical unit in width. To put this into perspective, 1 AU is the distance from the Sun to Earth. The largest asteroid in this belt, Vesta, measures a remarkable 525 kilometers in diameter, roughly the same as the distance between London and Belfast. On the other hand, many of the smaller objects are just a few tens of kilometers across. Despite the vastness of the asteroid belt, it contains only about 3% of the Moon's mass, a testament to how scattered and sparse the material is in this region. Beyond the asteroid belt lies the realm of the gas and ice giants: Jupiter, Saturn, Uranus, and Neptune. These massive worlds dominate the outer solar system, each with their own unique characteristics, from Jupiter's great red spot to Saturn's iconic rings. As we continue our journey past Neptune's orbit, which lies about $30 Australian from the Sun, we finally reach the Kuiper Belt, our destination. This icy expanse stretches from about $30 to $50 from the Sun and is home to a range of fascinating objects, from frozen remnants of the early solar system to dwarf planets such as Pluto, Haumea, Eris, Makemake, and many smaller objects. Like the asteroid belt, the Kuiper belt is considered a relic of the early solar system. The objects in the Kuiper belt are thought to be some of the oldest surviving pieces of the solar nebula, the cloud of gas and dust from which our sun and planets formed. At one point in the distant past, these objects could have coalesced into a new planet. However, the gravitational influence of Neptune prevented this from happening, leaving the Kuiper belt as a frozen region of debris rather than a collection of planets. Unlike the asteroid belt, which primarily consists of rocky materials, the Kuiper belt is made mostly of frozen methane, ammonia, and water ice. This frozen, thick, donut-shaped ring of debris holds hundreds of thousands of large icy bodies, many larger than 100 kilometers in diameter. Additionally, there are over 1 trillion comets and countless smaller pieces of debris scattered throughout. One of the most intriguing features of the Kuiper belt is the vast distances between its objects. On average, the objects in the Kuiper belt are spaced 0.02 to 0 Australian dollars and 10 cents apart, equivalent to distances of between 3 to 15 million kilometers. This enormous distance between objects helps to illustrate how isolated and sparsely populated this region is. Despite the relative emptiness, the Kuiper belt holds crucial clues about the origins of the planets and comets in our solar system, offering a window into the past that could help scientists piece together the history of our celestial neighborhood. These icy bodies, drifting silently in the outermost reaches of the solar system, offer researchers a unique opportunity to study some of the most primitive building blocks of the solar system. But the Kuiper belt isn't just one single structure. It's part of a broader, more complex system that stretches far beyond what we can easily observe. At the outer edges of the Kuiper belt lies an even more distant and less understood region known as the scattered disk. The scattered disk overlaps with the outer edges of the Kuiper belt, but its objects are in more highly elliptical orbits, some stretching out as far as 1,000 Australian dollars, with a few reaching even further. These scattered disk objects are more dynamically unstable, and their paths are often perturbed by the gravity of the giant planets, particularly Neptune. Beyond the scattered disk, there exists another colossal region called the Oort cloud. The Oort cloud is a spherical shell of icy debris that surrounds the entire solar system. It is theorized to extend from 2,000 to as far as 100,000 Australian dollars from the Sun, much farther than the Kuiper belt and the scattered disk. However, due to its extreme distance, the Oort cloud is incredibly difficult to observe directly. Unlike the Kuiper belt, which is donut-shaped, the Oort cloud is spherical, resembling a gigantic bubble of debris. Despite these differences, both the Kuiper belt and the Oort cloud serve as crucial sources of comets. The Kuiper belt is thought to be the birthplace of short-period comets, while the Oort cloud is the source of long-period comets, which take much longer to complete their orbits around the Sun. Interestingly, the Kuiper belt has undergone significant changes over time. Originally, it likely contained 7 to 10 times the mass of Earth. However, the gravitational forces exerted by the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, have caused much of the material in the Kuiper belt to be lost to space. Today, the mass of the Kuiper belt is only about 10% of Earth's mass, and the region continues to slowly erode over time. Objects occasionally collide, breaking apart into smaller fragments, and some of these fragments are expelled from the solar system by the solar wind. Others are pushed into orbits that bring them closer to the Sun, transforming them into short-period comets with orbits of less than 200 years. The comets that originate in the Kuiper belt can be spectacular sights to behold, especially when they pass close to the Sun. As they approach, the heat causes the icy bodies to release gas and dust, creating the bright tails we associate with comets. Some famous comets, like Halley's Comet, with an orbital period of 76 years, and Comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994, have their origins in the Kuiper belt. The collision of Shoemaker-Levy 9 with Jupiter was a momentous event, as it marked the first ever observed impact between two solar system bodies. While Jupiter survived the impact, the event was visible from Earth and provided scientists with invaluable data about planetary collisions. While the Kuiper belt remains a fascinating and rich frontier, it poses no immediate threat to Earth. In fact, the short-period comets originating from the Kuiper belt are not expected to pose any danger to Earth in the next 100 years or more. For example, despite recent reports about the near-Earth asteroid 2024 Y4, the chances of it colliding with Earth or the Moon are exceedingly small. So, while the Kuiper Belt remains a source of scientific interest, there is no need to worry about these objects in the foreseeable future. Despite being only a small remnant of its former self, the Kuiper Belt remains one of the most intriguing and expansive regions in the solar system. It offers an almost endless array of objects for exploration. Unlike the Oort cloud, which we have yet to visit, the Kuiper Belt has already been the subject of space exploration. NASA's New Horizons mission, which famously conducted a flyby of Pluto, is the only spacecraft to have visited the Kuiper Belt. In 2019, New Horizons made history by performing a flyby of another Kuiper Belt object, 2014 MU-69, which was later officially named Arrokoth. This flyby took place 1.5 billion kilometers beyond Pluto and was the most distant flyby in the history of space exploration. The flyby of Arrokoth revealed some surprising and unprecedented insights. Arrokoth, a small icy object in the Kuiper Belt, is a contact binary, a type of object composed of two distinct lobes that once merged to form a single body. Its unusual shape, resembling a flattened snowman, was unlike anything previously seen in our solar system. Despite its small size, just 35 kilometers long, 20 kilometers wide, and 10 kilometers thick, Arrokoth's unique structure has provided crucial insights into the process by which planetary building blocks come together. It has also helped scientists better understand how planets may have formed in the early solar system. Arrokoth's peculiar shape and rotation have led to groundbreaking conclusions about how planetesimals, small bodies that eventually come together to form planets, are created. Previously, scientists debated whether planetesimals formed through high-speed collisions, hierarchical accretion, or through a slower process in which nearby objects gradually clump together due to gravity, local cloud collapse. Thanks to New Horizons and the data gathered from Arrokoth, it is now clear that planetesimals formed through the latter process. The object's smooth surface and lack of fractures suggest that Arrokoth formed at low speeds, giving weight to the theory of local cloud collapse. In 2015, humanity witnessed a remarkable achievement in space exploration when NASA's New Horizons spacecraft completed its flyby of Pluto, allowing us to get a closer look at the distant dwarf planet and its moons like never before. This historic encounter was like opening a new chapter in our understanding of the solar system. The spacecraft sent back a treasure trove of data that continues to shape our knowledge of this mysterious world. Not only did we get to see stunning images of Pluto's surface, but the mission also provided us with detailed observations of its largest moon, Charon, as well as Pluto's smaller moons, Nix, Hydra, Kerberos, and Styx. One of the most iconic images from the New Horizons mission was the photograph of Pluto's heart-shaped surface region, also known as Tombaugh Regio. The heart-shaped feature is one of Pluto's most striking features, and it caught the imagination of scientists and the public alike. But there's much more to this heart-shaped region than meets the eye. The western lobe of this heart, named Sputnik Planitia, is a vast nitrogen glacier that stretches an incredible 1,000 kilometers wide and 4 kilometers deep. This makes it the largest known glacier in the solar system. It is composed primarily of nitrogen ice, which has been flowing and shifting across the surface of Pluto for millions of years. Interestingly, Sputnik Planitia is named after Sputnik 1, the first artificial satellite launched by the Soviet Union, in recognition of the significant role that space exploration has played in shaping our understanding of distant worlds. The eastern lobe of Pluto's heart, on the other hand, is made of a lighter-colored material, which is believed to be nitrogen that is transported from Sputnik Planitia and deposited as ice across the surface. This movement of nitrogen across the surface gives Pluto its distinct, heart-shaped appearance. But the science behind this feature goes much deeper than just its beauty. The New Horizons data revealed that Pluto's surface is far more complex than we ever imagined. For decades, Pluto was thought to be a cold, barren world with little more than a few craters and an icy surface. However, New Horizons revealed a vibrant, dynamic planet with a rich history and an active surface. The mission also shed light on the geological processes occurring on Pluto. The data suggested that there are ongoing interactions between Pluto's atmosphere and its surface. This finding indicated that the dwarf planet might still have a source of internal heat, which could support the existence of an underground ocean, possibly of water ice. One of the most exciting ideas that came from the mission was the possibility of an internal water ice ocean beneath Pluto's icy crust. This idea was initially proposed by planetary scientists after studying the heart-shaped region and its surrounding features, which suggested the potential for past or present subsurface activity. Interestingly, a more recent study led by astrophysicist Harry Valentine from the University of Bonn has proposed an alternative explanation for the formation of Pluto's heart-shaped feature. According to Valentine's research, the heart could have been caused by a low-velocity impact from a space object that collided with Pluto at an oblique angle. This impact would have left behind a large, elongated splatter of material, much like how a water balloon might explode when thrown across the ground. This concept, although quite different from the internal ocean hypothesis, still provides an exciting clue about the planet's history and the violent processes that may have shaped its surface. Regardless of the cause of its heart-shaped region, the data collected by New Horizons has significantly expanded our understanding of Pluto. The spacecraft not only gave us breathtaking images of Pluto's surface and its moon Charon but also provided us with data on Pluto's smaller moons, Nix, Hydra, Kerberos, and Styx. These moons, like Pluto itself, are made up of ice and rocky material, and their study provides valuable insight into the formation and evolution of the outer solar system. One of the more intriguing aspects of the mission was the close-up images of Pluto's moon Charon. Charon is a huge moon, almost half the size of Pluto, and the images revealed some surprising features on its surface. One of the most notable discoveries was the enormous equatorial tectonic belt found on Charon. This feature suggests that Charon may have once had an internal water ice ocean, much like Pluto. The evidence for this comes from the surface's apparent tectonic activity, which suggests that the moon's interior may have once been warmer than previously thought. This could have allowed for the existence of a subsurface ocean, which would have been crucial for the development of life, if life had ever existed there. As the New Horizons spacecraft continues its journey beyond Pluto, its data continues to provide new insights into the Kuiper Belt and beyond. The spacecraft is expected to exit the Kuiper Belt sometime between 2028 and 2029, marking the end of its current mission. Although there is no specific target for further flybys at the moment, it is possible that NASA may identify another object in the Kuiper Belt for New Horizons to study in the future. This could help us to further understand the composition and history of these distant objects. Additionally, advancements in technology such as the James Webb Space Telescope may provide new ways of analyzing the composition of Kuiper Belt objects and potentially lead to the discovery of new features or characteristics of distant worlds. In the distant future, we may even see robotic missions that could land on one of these mysterious objects or collect samples to bring back to Earth. The possibility of returning samples from the Kuiper Belt would be a monumental achievement in space exploration, as it would allow us to better understand the raw materials that were present during the formation of the solar system. These materials could hold clues about the origins of life and the conditions that existed in the early solar system. As technology continues to improve, future missions could delve even deeper into the Kuiper Belt, providing us with new insights into the formation and evolution of our solar system. The Kuiper Belt, with its icy objects and mysterious moons, holds a wealth of knowledge waiting to be discovered. One day we may even be able to unlock the long-held secrets of this frozen frontier, one icy world at a time. But the Kuiper Belt is not the only unexplored region in our solar system. Beyond the Kuiper Belt lies an even more mysterious and far-reaching area, the Oort cloud. This colossal structure begins at the outermost reaches of the solar system and extends far beyond the orbit of Neptune. The Oort cloud is believed to be a massive, spherical shell made up of billions, or even trillions, of icy objects that are scattered across the distant reaches of space. These objects are remnants from the early solar system, leftover building blocks from the formation of the planets and other celestial bodies. What makes the Oort cloud so intriguing is that it has never been directly observed. It is located far beyond the reach of even our most powerful telescopes, making it nearly impossible to study directly. However, scientists have inferred its existence based on the behavior of long-period comets, which come from all directions and have highly eccentric orbits. These comets are believed to originate from the Oort cloud, although the cloud itself remains largely invisible to us. The Oort cloud was first proposed in 1950 by Dutch astronomer Jan Oort, who theorized that it was the source of long-period comets. These comets, which can take hundreds of thousands or even millions of years to complete an orbit around the Sun, often come from directions that are difficult to explain using the known regions of the solar system. Oort noticed that the orbits of these comets seem to cluster around a specific distance from the Sun, about 50,000 astronomical units, AU. This clustering suggested that these comets were coming from a distant, spherical cloud of icy debris, and that the Oort cloud was the most likely source. The Oort cloud is thought to be a remnant of the early solar system, containing leftover planetesimals that were scattered by the gravity of the newly formed planets. Some of these objects were flung into the outer reaches of the solar system, where they became part of the Oort cloud. The objects in the cloud are believed to be mostly icy bodies that have remained frozen for billions of years. When these objects are disturbed by the gravitational influence of nearby stars or other forces in the galaxy, they are sent on a path that takes them toward the inner solar system, where they become comets. The Oort cloud is also thought to be the source of many of the comets that we observe today. These comets, which have long orbital periods and unpredictable paths, are believed to be remnants of the primordial material that once filled the solar system. When these comets are nudged by the gravity of other stars or objects in the galaxy, they are sent on a collision course with the Sun, where they develop the characteristic glowing tail and coma that we associate with comets. Though the Oort cloud has never been directly observed, its existence is supported by mathematical models and the observed behavior of long-period comets. It is believed to be a spherical region that extends as far as 100,000 Australian dollars from the Sun. The objects within the Oort cloud are believed to be mostly icy, rocky bodies, ranging in size from small chunks of ice to larger planetesimals. These objects are thought to be remnants of the early solar system, trapped in the far reaches of space. In the coming years, advancements in technology may allow us to study the Oort cloud in greater detail. New telescopes and space missions could potentially detect the faint signals of objects within the cloud, providing us with the first direct evidence of this distant region. The Oort cloud remains one of the last great frontiers of space exploration, a region that holds secrets about the early history of the solar system and the processes that led to the formation of planets and other celestial bodies. In conclusion, while the Oort cloud remains a mysterious and largely uncharted area of the solar system, it offers a tantalizing glimpse into the early history of our cosmic neighborhood. The cloud, made up of billions of icy objects, is believed to be the source of long-period comets and holds valuable clues about the formation of the solar system. As technology continues to advance, we may one day be able to unlock the secrets of the Oort cloud, revealing more about the distant reaches of our solar system and the objects that reside there. It is a frontier that still holds many mysteries, waiting to be discovered by future generations of astronomers and space explorers. The gravitational forces acting on objects in our solar system are incredibly complex, with many influences coming from sources outside our Sun's immediate reach. The mysterious Oort cloud, which is believed to be a spherical shell surrounding our solar system, is a fascinating example of this. The Oort cloud is thought to contain a vast collection of icy chunks and objects, some of which are scattered into long elliptical orbits, forming long-period comets. These comets, which take hundreds or even thousands of years to complete one orbit around the Sun, are a testament to the intricate gravitational interactions that shape our solar system. The question of how these billions or even trillions of icy bodies came to be part of the Oort cloud is tied directly to the gravitational perturbations that have occurred throughout the history of the solar system. It's widely accepted that the Oort cloud's formation can be attributed to gravitational forces acting on objects that were once part of the more familiar Kuiper belt. The Kuiper belt, located beyond the orbit of Neptune, is home to numerous icy bodies, dwarf planets, and comets. When objects in the Kuiper belt are affected by gravitational interactions with other celestial bodies or objects, they can be displaced from their original positions. These gravitational perturbations may be responsible for ejecting some objects from the Kuiper belt and sending them toward the distant reaches of the Oort cloud. While the Kuiper belt mainly contains short-period comets, the long-period comets that originate in the Oort cloud are thought to be the result of these distant, yet powerful, gravitational influences. Interestingly, it's believed that the gravitational disturbances causing the long-period comets' trajectories could come from a variety of sources. These disturbances may occur due to the influence of passing stars, molecular clouds, or even the tidal forces from the Milky Way galaxy itself. One of the more intriguing examples of this occurred around 70,000 years ago, when a star known as Schultz's star came very close to our solar system. In fact, it passed through the outer region of the Oort cloud, but despite its proximity, it didn't cause any significant disruptions to the cloud itself or the solar system in general. Schultz's star is a binary system composed of a red dwarf and a brown dwarf companion, both low-mass stars. Despite its relative closeness to the solar system, the gravitational influence of Schultz's star on the Oort cloud was much weaker compared to the effect of our much larger Sun. However, even with this diminished gravitational pull, simulations conducted in 2018 suggested that Schultz's star had a noticeable impact on the trajectories of some objects within the Oort cloud. This may have nudged certain bodies, pushing them into new paths that eventually led to their classification as long-period comets. This encounter with Schultz's star, while fascinating, is only one example of the many gravitational interactions that have likely occurred over the solar system's 4.6 billion-year history. The sheer length of time our solar system has existed means that it has been subject to many close encounters with passing stars. These interactions might have played a role in shaping the Oort cloud into the structure we believe it to be today. However, most models of the Oort cloud suggest that it has been able to form and remain intact despite these numerous encounters. Over the eons, it's likely that material from the Oort cloud could have been exchanged with other nearby stars, possibly even being shared or redistributed among them. One of the more intriguing theories about the Oort cloud suggests that there could be similar clouds of icy objects orbiting other stars in the galaxy. These clouds would likely have the same formation process as our Oort cloud, with gravitational forces from nearby stars influencing the trajectories of icy bodies. This has led some scientists to propose that the Oort cloud may not be a unique feature of our solar system but could be part of a broader galactic phenomenon. The structure of the Oort cloud itself is also a subject of much debate. Some researchers believe that the Oort cloud consists of two distinct regions, each with its own unique shape and characteristics. The inner region may resemble a disk, similar to the shape of the Kuiper belt, while the outer region may take on the spherical shell-like structure typically associated with the Oort cloud. According to some models, the inner edge of the Oort cloud may be around 2,000 astronomical units (AU) from the Sun, while its outer edge could extend all the way to the far reaches of interstellar space, potentially reaching 100,000 Australian dollars from the Sun. If these distances are accurate, the Oort cloud could span more than 1.5 light-years across. To put this into perspective, it's worth considering the journey of Voyager 2, a spacecraft launched in 1977 to explore the outer planets of our solar system. As of now, Voyager 2 is about 139 Australian dollars away from the Sun, having traveled at a speed of about 56,000 kilometers per hour. Despite being the second farthest human-made object from Earth, Voyager 2 would still need to travel another 300 years just to reach the innermost edge of the Oort cloud. Even if it were to continue on its path, it would take another 30,000 years to traverse the entire Oort cloud. At such vast distances, it's no wonder that we have yet to make direct observations of this distant region of our solar system. The challenge of interstellar space travel becomes clear when you consider that our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. Even with the fastest spacecraft, the journey to even the closest stars would take thousands of years. But despite the technological and logistical challenges, we continue to push forward in our quest to explore the unknown. Voyager 2, after leaving the protective bubble of the heliosphere, entered interstellar space in 2018, providing invaluable data about the environment beyond our Sun's influence. Still, some astronomers question whether the Oort cloud truly exists, mainly because we've never been able to directly observe it. This uncertainty has led to some alternative hypotheses about where long-period comets might originate. For instance, in 2019, an interstellar comet known as Borisov was observed as it passed through our solar system. Comet Borisov was unique because it was the first comet discovered to originate from outside our solar system. This finding prompted some scientists to suggest that long-period comets may come from interstellar space, rather than from the Oort cloud. However, the majority of astronomers continue to support the existence of the Oort cloud, despite the lack of direct observation. Indirect evidence, such as the observed behavior of long-period comets and the results of numerous mathematical models, strongly suggest that the Oort cloud is indeed real. While we may not be able to directly see it with our current technology, the weight of indirect evidence continues to grow. This situation is reminiscent of past scientific breakthroughs, such as the development of the heliocentric model of the solar system by Copernicus and Galileo. At the time, their ideas were controversial and lacked direct observational support, yet over time they were proven correct. In the future, as technology improves, we may eventually be able to directly observe the Oort cloud and confirm its existence beyond a shadow of a doubt. Perhaps future generations of astronomers will discover even more about the cloud's structure and its role in the formation of comets. Until then, the Oort cloud remains one of the most intriguing and mysterious features of our solar system, continuing to fuel our curiosity and wonder about the cosmos. Asteroids are classified based on their spectrum or color, which often indicates their composition. There are 3 primary spectral categories: the C group, which consists of dark carbonaceous asteroids, the S type, made up of stony or siliceous asteroids, and the M types, which are metallic asteroids. While other variations exist, these 3 groups are the most common. We might touch upon some of these variations later in the video, but they all fall within these categories. Let's now dive into the top 10 most interesting asteroids. Starting with 2005 VX3, this minor planet boasts the largest aphelion known to us. At its closest approach to the Sun, it's only 4 Australian dollars and 10 cents away, which places it inside Jupiter's orbit. However, when it's furthest from the Sun, it can reach a massive heliocentric distance of about 3,000 Australian dollars. This makes it the asteroid with the largest orbital eccentricity. The last time it was observed was in January 2006, when it reached perihelion, and it won't be seen again for another 30 to 40,000 years. This asteroid is likely a dormant comet, having lost its volatile icy materials after making previous close approaches to the Sun. As a result, it has no tail, which is why it isn't recognized as a comet. It is estimated to be about 7 kilometers in diameter. Next up is 99,942 Apophis, a near-Earth asteroid that caused a bit of a stir in December 2004. Initial observations indicated a 2.7% chance that it would collide with Earth on April 13, 2029. Fortunately, further observations clarified its orbit and removed the threat of an impact in 2029. However, there is still a possibility that Apophis could pass through a small region of space called a gravitational keyhole during its close encounter with Earth. This could alter its orbit enough to set it on a collision course with Earth in 2036. Although the chances of this happening are now extremely small, Apophis held the record for the highest rating on the Torino impact scale, reaching level 4 at one point. If it had hit Earth, the estimated kinetic energy would have been around 750 megatons, roughly 13 times more powerful than the largest hydrogen bomb ever detonated. Apophis is a stony, S-type asteroid, with the most recent observation in 2013 estimating its size to be about 325 meters across. Interestingly, asteroids the size of Apophis are expected to hit Earth about once every 80,000 years, so let's hope the next one isn't too soon. At number 8 we have 25143 Itokawa, a Mars-crossing asteroid. This means it crosses inside Mars' orbit, and it was the first asteroid to be the target of a sample return mission by the Japanese space probe Hayabusa. At 500 meters in diameter, Itokawa is the smallest asteroid ever to be photographed by a spacecraft. It is an S-type asteroid and may even be a contact binary, two separate asteroids that merged over time. Its surface is covered with boulders and has very few impact craters, suggesting it is a giant rubble pile. Its average density is about 1.8 grams per cubic centimeter, which means it isn't solid rock but a collection of fragments that have built up over time. Interestingly, the asteroid's gravity is too weak to allow a spacecraft to orbit it, so the Hayabusa probe had to park next to Itokawa and orbit the Sun alongside it. In 2010, Hayabusa successfully landed on Itokawa and returned dust samples from its surface. Number 7 on our list is 2 Pallas, discovered shortly after Ceres in the early 1800s. In fact, astronomers were initially searching for Ceres when they stumbled upon Pallas. At the time, Pallas was considered a planet, as were many asteroids, before the discovery of more asteroids led to their reclassification as minor planets. Pallas is one of the largest asteroids in the solar system, comprising about 7% of the mass of the asteroid belt. Its diameter of 544 kilometers makes it slightly larger than Vesta, although it is less massive, about 10 to 30% less. Pallas is a C-group asteroid, meaning it has a dark surface that reflects only about 4% of the light falling on it, similar to fresh asphalt. Its orbit is inclined at 34.8 degrees to the plane of the solar system, making it practically inaccessible to spacecraft hoping to study it in more detail. Moving on to number 6, we have 10,199 Chariklo, which technically shouldn't be on this list since it's a centaur, a type of minor planet that orbits between the outer planets. Chariklo, however, is notable for having a ring system, much like Saturn though on a much smaller scale. Discovered in 2013, it has 2 rings, one 7 kilometers wide and the other 3 kilometers wide, with a separation of about 9 kilometers. This makes Chariklo the smallest known object to possess rings. Interestingly, these rings shouldn't be stable due to the small size of Chariklo, suggesting that they are actively maintained by shepherd moons, or they could eventually dissipate over millions of years. Number 5 on our list is Leticia, a large M-type asteroid. It has a retrograde rotation and is located in the asteroid belt, measuring about 100 kilometers in diameter. Leticia stands out due to its unusually high density, estimated at 3.4 grams per cubic centimeter, suggesting it's made of metal-rich rock. However, there is little evidence of metal on its surface, and it resembles a C-type asteroid in appearance. Some scientists speculate that the asteroid has a metal-rich core surrounded by a layer of rubble, with craters on its surface showing softened outlines that support this theory. Leticia's irregular shape and heavily cratered surface, with the largest impact crater spanning 45 kilometers, make it an intriguing object to study. At number 4 we find 433 Eros, an S-type asteroid that is approximately 34 kilometers long. Eros is the second largest near-Earth asteroid, after 1036 Ganymede. It's also a Mars-crossing asteroid, meaning it crosses inside Mars' orbit. Eros is interesting because its orbit can only remain there for a few hundred million years before being perturbed by Mars' gravity. Eventually, Eros could evolve into an Earth-crossing asteroid with a potential impact in about 2 million years. The data from NASA's Near Shoemaker probe, which visited Eros in 1998 and 2000, suggested that the asteroid contains roughly 20 billion tons of rare metals, including gold and platinum. Number 3 on our list is 243 Ida, a stony, S-type asteroid located in the asteroid belt. In 1993, Ida was visited by the Galileo spacecraft on its way to Jupiter. Ida is irregularly shaped, with an average diameter of 31.4 kilometers, and has one of the most heavily cratered surfaces in the solar system. Its density is about 2.66 grams per cubic centimeter, and despite its weak gravity, jumping from one end of the asteroid to the other would be easy if you could exceed 20 meters per second, allowing you to escape its gravity. Ida also has a moon, Dactyl, which was discovered by Galileo during its flyby. Asteroids are also classified based on their spectrum or color, which often indicates what the asteroid is made of. There are 3 main spectral categories that most asteroids fall into. These include the C group, which are dark, carbonaceous asteroids, the S-type, which are stony or siliceous asteroids, and the M-types, which are metallic asteroids. While other types exist, these 3 are the most common. We may mention a few other variations as we move forward, but these groups are essentially the main categories to keep in mind. Now let's count down the top 10 most interesting asteroids. At number 10 we have 2005 VX3. This minor planet has the largest aphelion, the farthest point in its orbit from the Sun, of any known minor planet. At its closest approach to the Sun, it's only $4.10 away, which places it inside the orbit of Jupiter. However, when it's furthest from the Sun, it has an incredible estimated heliocentric distance of 3,000 Australian dollars. This vast orbit means it has the largest orbital eccentricity of any known minor planet. The last time it was observed was in January 2006, and it won't be seen again for another 30,000 to 40,000 years. This asteroid might be a dormant comet, as it likely lost most of its icy materials from past close encounters with the Sun. It is estimated to be about 7 kilometers in diameter. Number 9 on the list is 99942 Apophis, a near-Earth asteroid that caused a stir in December 2004 when initial observations suggested there was a 2.7% chance it could hit Earth on April 13, 2029. But don't worry, further observations improved the prediction, ruling out any collision in 2029. There was a lingering concern that during this very close encounter, Apophis could pass through a gravitational keyhole, a tiny region less than 800 meters wide that would alter its orbit. This could have led to a future impact scenario in 2036, but in 2006, the chance of this occurring was deemed very small. Apophis made history by achieving the highest rating on the Torino impact scale, reaching a level 4 at one point. If it had struck Earth, the estimated kinetic energy would have been about 750 megatons, 13 times more powerful than the largest hydrogen bomb ever detonated. Apophis is a stony S-type asteroid, and the most recent observation in 2013 estimated it to be around 325 meters across. Asteroids like Apophis are expected to hit Earth every 80,000 years on average, so let's hope the next one isn't too soon. Next we have 25143 Itokawa, a Mars-crossing asteroid. This asteroid is famous for being the target of Japan's Hayabusa space mission, which successfully returned samples from its surface. Itokawa is the smallest asteroid ever to be photographed by a spacecraft, measuring just 500 meters across at its longest point. It is an S-type asteroid and may be a contact binary, which means it's likely 2 separate asteroids that have merged over time. The surface of Itokawa is covered in boulders, forming a massive rubble pile. Its density is estimated at 1.8 grams per cubic centimeter, suggesting it's not solid rock but rather fragments of gravel. Its low gravity was not strong enough to let the Hayabusa spacecraft orbit around it, so the spacecraft orbited the Sun alongside the asteroid. In 2010, Hayabusa successfully landed on Itokawa and brought dust samples back to Earth. At number 7 is 2 Pallas. This asteroid was discovered just after Ceres in the early 1800s. While astronomers were searching for Ceres, they accidentally found Pallas, which was near Ceres at the time. When Pallas was first discovered, it was classified as a planet just like other asteroids at the time. Over the years, as more asteroids were discovered, they were reclassified as minor planets. Pallas is one of the largest asteroids in the solar system, comprising 7% of the mass of the asteroid belt. With a diameter of 544 kilometers, it's slightly larger than Vesta but about 10 to 30% less massive, making it the third largest asteroid by mass. Pallas is a C-type asteroid with a very low albedo, meaning it has a dark surface. This asteroid reflects only about 4% of the light that hits it, which is similar to fresh asphalt. At its brightest, it can be seen through binoculars, but it's not visible to the naked eye. Pallas' orbit is inclined at 34.8 degrees to the plane of the solar system, making it practically inaccessible for spacecraft to investigate closely. Next, we have 10199 Chariklo, a centaur that orbits between Uranus and Saturn. Despite being a centaur, Chariklo has an extraordinary ring system, making it stand out on this list. Chariklo is over 300 kilometers in diameter and has two rings, one 7 kilometers wide and the other 3 kilometers wide, located about 9 kilometers apart. These rings are the smallest known to exist around any object. Interestingly, due to Chariklo's small size, these rings shouldn't be stable unless they are actively contained by shepherd moons. Otherwise, they will gradually fade and dissipate over the next few million years. Leticia, an M-type asteroid, ranks number 5 on our list. It has a retrograde rotation and is found in the asteroid belt. Measuring about 100 kilometers in diameter, Leticia has one of the highest densities of any observed asteroid, around 3.4 grams per cubic centimeter, suggesting it is made of metal-rich rock. However, despite its high density, there's little evidence of metals on the surface, and it has the color of a carbonaceous asteroid. The theory is that Leticia has a metallic core surrounded by a thick layer of rubble, which is why its surface looks different than expected. It is also heavily cratered, with the largest impact crater measuring 45 kilometers in diameter. 433 Eros, at number 4, is another Mars-crossing asteroid. With a length of about 34 kilometers, Eros is the second largest near-Earth asteroid after Ganymede. It was the first asteroid to be visited by a spacecraft, and in 2001, NASA's Near Shoemaker probe landed on its surface. Eros' orbit is unstable, which means it may eventually evolve into an Earth-crossing asteroid, potentially becoming a future impactor. On average, impacts of this size occur every 2 million years. During its visit, the Near Shoemaker probe collected valuable data, suggesting that Eros contains 20 billion tons of rare metals, such as gold and platinum. 243 Ida, at number 3, is an S-type asteroid found in the asteroid belt. It was visited by NASA's Galileo spacecraft in 1993. Ida has an average diameter of 31.4 kilometers and is irregularly shaped, made up of two large objects connected together. Its surface is heavily cratered, and it has a density of around 2.66 grams per cubic centimeter. What makes Ida particularly fascinating is its moon, Dactyl. This moon, which is only 1.4 kilometers in diameter, is about 120th the size of Ida. It was named after the dactyls of Greek mythology. Dactyl and Ida share many characteristics, suggesting they came from the same place. Ida is the only asteroid that has been photographed in high definition with its moon. At number 2 is Vesta, the second most massive object in the asteroid belt. Vesta, with a diameter of 525 kilometers, is a rocky protoplanet and one of the brightest objects in the asteroid belt. It is the only asteroid that has a differentiated interior, similar to the terrestrial planets. Vesta is home to the tallest mountain in the solar system, called Rhea Silvia. NASA's Dawn spacecraft visited Vesta in 2011, gathering a wealth of data that researchers are still analyzing years later. Finally, at number 1, is Ceres, the only dwarf planet in the asteroid belt. Ceres, which has a diameter of 960 kilometers, accounts for about 1/3 of the mass of the entire asteroid belt. It is the largest object in the belt and is the only one rounded by its own gravity. Ceres is believed to have a rocky core and an icy crust, with a potential remnant internal ocean of liquid water. Its surface likely consists of a mixture of water ice, carbonates, and clay. In 2015, NASA's Dawn spacecraft arrived at Ceres and discovered bright spots inside a crater, believed to be highly reflective materials containing ice or salts. These findings have given us a glimpse into the mysterious world of Ceres, offering new insights into the early solar system, discovered by Galileo during its flyby. Asteroids are also classified based on their spectrum or color, which often indicates what the asteroid is made of. There are three main spectral categories that most asteroids fall into. These include the C group, which are dark, carbonaceous asteroids, the S type, which are stony or siliceous asteroids, and the M types, which are metallic asteroids. While other types exist, these three are the most common. We may mention a few other variations as we move forward, but these groups are essentially the main categories to keep in mind. Now let's count down the top 10 most interesting asteroids. At number 10 we have 2005 VX3. This minor planet has the largest aphelion, the farthest point in its orbit from the Sun, of any known minor planet. At its closest approach to the Sun, it's only $4.10 away, which places it inside the orbit of Jupiter. However, when it's furthest from the Sun, it has an incredible estimated heliocentric distance of 3,000 Australian dollars. This vast orbit means it has the largest orbital eccentricity of any known minor planet. The last time it was observed was in January 2006, and it won't be seen again for another 30,000 to 40,000 years. This asteroid might be a dormant comet, as it likely lost most of its icy materials from past close encounters with the Sun. It is estimated to be about 7 kilometers in diameter. Number 9 on the list is 99942 Apophis, a near-Earth asteroid that caused a stir in December 2004 when initial observations suggested there was a 2.7% chance it could hit Earth on April 13, 2029. But don't worry, further observations improved the prediction, ruling out any collision in 2029. There was a lingering concern that during this very close encounter, Apophis could pass through a gravitational keyhole, a tiny region less than 800 meters wide that would alter its orbit. This could have led to a future impact scenario in 2036, but in 2006, the chance of this occurring was deemed very small. Apophis made history by achieving the highest rating on the Torino impact scale, reaching a level 4 at one point. If it had struck Earth, the estimated kinetic energy would have been about 750 megatons, 13 times more powerful than the largest hydrogen bomb ever detonated. Apophis is a